Hello chemistry students, Dr. Tullis here, and we are starting chapter 6 looking at the structure of atoms. Our first section we are looking at the relationship between wavelength and frequency of electromagnetic radiation and the speed of light, and looking at the relative wavelength or frequency of various types of electromagnetic radiation. So back in chapter 2, we described atoms as consisting of protons, neutrons, and electrons. Protons and neutrons are located in that very dense nucleus, and the electrons are in the space that's around the nucleus. But in this chapter and the next, we look at the arrangement of electrons in atoms in a lot more detail. There are experiments looking at the interaction between atoms and electromagnetic radiations, and this was essential to developing theories about the electronic structure of atoms. And to understand these experiments, we first need to describe the features of electromagnetic radiation. When atoms gain energy, they become excited. Added energy is absorbed by electrons and then released in the form of electromagnetic radiation. Electromagnetic radiation, or light, is composed of two orthogonal vectors, an oscillating electric wave and a magnetic wave traveling through space like this picture shows. Electromagnetic radiation travels at the same rate, the speed of light in a vacuum. It doesn't matter if we're talking about X-rays or radio waves or visible light or ultraviolet light. The speed of light is 2.998 times 10 to the 8th meters per second, which is equivalent to 186,000 miles per second. Electromagnetic radiation is characterized by its wavelength and its frequency. So we use this equation here. Speed is equal to wavelength times frequency. Just be aware that throughout this chapter, frequency may also be referred to as V. So F and V you might find to be interchangeable. So this lambda is wavelength. We typically describe wavelength in nanometers, simply because, I'm going to flip to the next page here, our nanometers on this visible spectrum range from about 400 nanometers to about 700 nanometers, but that is something that we will convert to from meters because our speed of light is in meters per second. So obviously when we're doing our math, we need to have our wavelength in meters, but we can convert it to nanometers pretty easily to see what color it corresponds with. And then we have frequency. Frequency describes how frequent a wave occurs per second. So if I have a greater frequency, that means that I'm having a lot of waves per second. My wavelength measures the distance from the crest of one wave to the crest of another wave, or the trough of one wave to the trough of another wave, or from one position on one wave to the same position on the next wave. Here is our electromagnetic radiation spectrum. Again, looking all the way from our gamma rays to our radio waves. Our radio waves are long wavelengths, low energy. And as I go to the left, the energy increases, which means the frequency of a wave increases and the wavelength decreases. Let's try calculating the wavelength of a radio wave from WOXY that has a frequency of 97.7 megahertz. Knowing this equation, speed equals wavelength times frequency, and also knowing that mega means that there's 1,000,000 hertz in a megahertz. Here's how I set it up. I first converted my megahertz into hertz, and that 1 megahertz is equal to 1,000,000 hertz, so that gave me my frequency in hertz. Then using speed equals wavelength times frequency, I rearranged the equation to solve for wavelength. So speed divided by frequency, the speed of light is always 2.998 times 10 to the 8th meters per second, divided by my 97,700,000 hertz, and I got a wavelength of 3.07 meters. Let's look at the second problem. We're told that we need to find a cell phone signal that is operating at 1.12 gigahertz. Knowing that giga stands for 1 times 10 to the 9th hertz. Let's see how you did it. The wavelength is again equal to speed divided by frequency. So 2.998 times 10 to the 8th meters per second divided by 1.12 times 10 to the 9th hertz. Hertz can also be described as 1/seconds. That gives us 0.268 meters. Here's a few I'd like you to try. The highest frequency would be violet, and the lowest frequency would be red. The wavelength of radiation in a microwave is shorter than FM radio wavelength. And if I were to just go back here to our chart here, if I looked at my FM radio waves versus microwaves, we can see that the radio waves have less energy, which means a longer wavelength. So a microwave has shorter wavelengths. The wavelengths of X-rays are going to be shorter than the wavelengths of UV light. And if I want to find the frequency of green light, I'm going to take the speed of light divided by the wavelength. Again, my wavelength needs to be in meters, going from nanometers to meters. There is 10 to the 9th nanometers in 1 meter. So we should get 5.88 times 10 to the 14th. You can write hertz, or you can just write 1/s, or you can write inverse seconds. Those are all the same units. Which of the following produces radiation of the highest frequency? What do you think? Hopefully you said a red laser pointer. Number 2, which of the following radiation has the longest wavelength? Hopefully you said radio waves. Pause the video here to try to find the wavelength of 98.6 megahertz in centimeters. Here's my work. I went from megahertz to hertz, knowing that there's a million hertz and a mega, like a mega millions. So I got 9.86 times 10 to the 7th hertz. To find wavelength, I did speed divided by frequency to get 3.04 meters, and then I converted from meters to centimeters, so I got 304 centimeters. Which of the following types of radiation has the highest energy? That would be gamma rays. Now calculate the frequency of orange light with a wavelength of 595 nanometers. Here's my work. I went from nanometers to meters, giving me 5.95 times 10 to the negative 7 meters. And then when I plugged it into my speed equals wavelength times frequency, solving for frequency is speed divided by wavelength. And that gave me 5.04 times 10 to the 14th hertz. And we're moving on to section 2. We're going to look at this photoelectric effect and understand that energy of a photon, which is a massless particle of radiation, is proportional to its frequency. If you were told that you could drive your car at 23.4 miles per hour or 28.9 miles per hour or 34.2 miles per hour, but never any speed between these values, you wouldn't believe it. But they discovered this about electrons and atoms. Think about walking up a flight of stairs. Here's the potential energy of a person walking up a ramp. It increases in a uniform, continuous manner. But now think about if you're walking upstairs. Your foot is either on one step or the other step. You can't step in between the steps. Well, Max Planck explained it by assuming that energy comes in packets of energy called quanta. Similar to rungs on a ladder. You're either on one step or you're on the next step of the ladder. Or notes on a piano. You're either C or C sharp. There's nowhere in between. Like I said, Max Planck proposed that light, heat, and other forms of radiation come in tiny bundles, which he calls quanta. He proposed that the energy is quantized. Quantization means that only certain energies are allowed. The amount of energy in a single particle, he said, depends on the frequency and can be given by the following equation. E equals hv, where v is the frequency of the wave. There we go. I told you that F and V are going to be interchangeable, but they are both frequency. So V is the frequency of the wave, and H is a constant that came to be called Planck's constant. He said an object can gain or lose energy by absorbing or emitting energy in quanta. A quanta of energy is the smallest unit of energy that may be exchanged between oscillators or emitted as radiation. It is too small to be observed in the classical world in which we live. Again, here is our energy is equal to HF, and H, write this down, is Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds. Now I want to do a little bit of connecting. we said that E energy was equal to Planck's constant times frequency. And frequency, we also said we would refer to it as V. So E equals HV or E equals HF. And we just said earlier the speed was equal to wavelength times frequency. Well, if I were to move these variables around to solve for F is equal to C divided by wavelength, which is this. I could essentially plug my frequency that I've just found into this equation and say that energy is equal to Planck's constant times the speed of light divided by wavelength. As the frequency of light increases, the energy of the photon increases. We would also find that as the wavelength of light increases, the energy of the photon decreases. Blue light has more energy than red light with a lower frequency. We then are introduced to the photoelectric effect. Shortly after Planck's work, Einstein incorporated his ideas into an explanation of the photoelectric effect and changed the description of electromagnetic radiation. Electrons are ejected when light strikes the surface of a metal, but only if the frequency of the light is high enough. The energy of the light must exceed a minimum or a threshold energy for this to occur. Any excess energy beyond this minimum goes into the kinetic energy of the ejected electron, and they fly away with a greater velocity.
That Einstein's work showed that only light above a certain frequency could eject an electron, regardless of the intensity of the beam. And for this reason, he proposed that light was comprised of individual quanta called photons, whereby it was an individual photon of sufficient energy equal to h times f that was able to eject an electron. This meant a number of things. First, it wasn't just the vibrational energy of the atoms in the black body that was quantized. Light is also quantized, since photons are quanta. So quantization seemed to be here to stay.
Sometimes light seems to act as a wave, and sometimes light seems to act as a particle. And an example of this would be the photoelectric effect, as described by Einstein. So let's say you had a piece of metal, and we know the metal has electrons. I'm going to go ahead and draw one electron in here. And this electron is bound to the metal because it's attracted to the positive charges in the nucleus. If you shine a light on the metal, so the right kind of light with the right kind of frequency, you can actually knock some of those electrons loose, which causes a current of electrons to flow. So this is kind of like a collision between two particles, if we think about light as being a particle. So I'm going to draw in a particle of light, which we call a photon. So this is massless. And the photon is going to hit this electron. And if the photon has enough energy, it can free the electron, right? So it can knock it loose. And so let me go ahead and show that. So here we're showing the electron being knocked loose. And so the electron's moving in, let's just say this direction with some velocity v. And if the electron has mass m, we know that there's a kinetic energy, right? The kinetic energy of the electron would be equal to 1/2 mv squared. This freed electron is usually referred to now as a photoelectron. So one photon creates one photoelectron. So one particle hits another particle.
Now that we got that explanation, I want to show you some more. Here's another picture of showing that incoming light with wavelength and frequency of whatever this is. We'll say this is red light. And it hits the metal, and if it's got enough frequency, enough energy, it can knock those electrons loose. Here we're able to see that we have light hitting this metal. But this is a material that ejects electrons if struck by photons of light of sufficient energy. This is not showing any reflection of electrons. Ejected electrons move to the anode. If here we have high frequency of light, we can see that there is electrons that have bounced off, and that is when light with a greater frequency than the critical frequency that is being used, we have the excess energy of the photon allows the electron to escape the atom with greater velocity. Here we have even higher intensity of light. It causes more electrons to be released from the surface. And again, we can use this anode here to measure. This first one, we had no readings. The second one, we were, midway there. In this last one with high intensity light, we can see our reading from the anode giving us this high intensity light. So it's showing us that there are lots of electrons, lots of current flowing. So there is a one-to-one correspondence between ejected electrons and light waves. This can only occur if light consists of individual units called photons, which is a packet of light in discrete energy. Here we can see here that there is no emission because this energy hitting that metal is not hitting that threshold frequency. Here we can see that we have low energy light. So it's hit the threshold frequency, and we can see that there are some electrons being emitted, low energy. High energy light hitting, we can see that there is higher energy of electrons, those photoelectrons being emitted. Classical theory suggests that energy of an ejected electron should increase with an increase in light intensity. This, however, is not experimentally observed. No ejected electrons were observed until light of a certain minimum energy is applied. Here we can see here, low energy, nothing is being kicked off of that metal. A little bit higher, some even greater intensity, a lot more greater energy. Demonstrated that light, usually considered to be a wave, can also have properties of particles, albeit without mass. That's why it's called a photon. It does not have mass. For each metal, there's that threshold wavelength. Cesium, for example, can emit electrons with red light. Some other metals require yellow light or even ultraviolet to emit. Here we can see here that this metal, when 700 nanometers, 1.77 electrovolts hit this metal, no electrons are being emitted. And then we can see here the velocity of the photon being emitted versus even more energy, and we have even a greater velocity. Let's try to do this problem. That you are an engineer that is designing a switch that works via the photoelectric effect. The metal used requires 6.7 times 10 to the negative 19th joules per atom to eject electrons. Will the switch work with light of 540 nanometers or greater? Why or why not? Using this equation, we know Planck's constant, and we know E equals hv. And we can plug in the frequency. We know that frequency is equal to speed divided by wavelength. So we can then say that E is equal to Planck's constant times the speed of light divided by wavelength. We're given the wavelength. Make sure you convert it into meters and plug that into your wavelength. We know H and we know C. See what kind of energy is required. Again, I put 540 nanometers into meters. I got 3.7 times 10 to the negative 19th joules. Now 3.7 times 10 to the negative 19th joules is less than 6.7 times 10 to the negative 19th, given that that metal requires. Because this energy is less than what is required to eject electrons, nope, that switch will not work. There will be no ejection of electrons. If I wanted to find out the wavelength of light needed, I would plug this in for my energy, and I would solve for wavelength. And if I did that, it would tell me that I would need a wavelength of at least 297 nanometers to emit electrons. Let's look at the photoelectric effect evidence for quanta. Let's say that we're looking at a carnival game and you want to knock down the bottles. What would you choose? Would you hit those bottles with 50 Nerf balls or with one baseball? Well, 50 Nerf balls would be very intense. But those are small balls, they're lightweight, versus one baseball. It's obviously larger and it's heavier, and there's going to be more energy. Think about playing a video game. Let's say it takes a quarter to play a video game, but you've got a bunch of nickels and dimes. No matter how many, you're not going to get a video game to work if you need 1/4 that's required. So let's look at this problem. DVD players use lasers that emit red light with a wavelength of 640 nanometers. What is the energy of one photon of this light? What is the energy of 1 mole of photons of red light? Let's work through it. 640 nanometers. Again, anytime I see nanometers, I want to get to meters. There's 10 to the 9th nanometers in 1 meter. So that would be 6.4 times 10 to the negative 7th meters. I'm going to plug it in to my speed equals wavelength times frequency equation to solve for frequency. I'm going to do speed divided by wavelength. That gave me 4.68 times 10 to the 14th hertz. Then I'm going to plug it into my E equals hv equation. Could I do it all at once? Absolutely. I just separated it. So I plugged in my Planck's constant, h, times the frequency, which I just found, and I got an energy of 3.1 times 10 to the negative 19th joules per photon. The next step to get me for 1 mole, I took that joules per photon, and there's 6.022 times 10 to the 23rd photons in 1 mole. So that would be 1.9 times 10 to the 5th joules per mole. We could also divide that by 1,000 and get kilojoules per mole. How about you try to set this one up? Calculate the energy per mole of photons for the laser used in Blu-ray players, which has a wavelength of 405 nanometers. Pause the video here, see if you can set that up. First, I went from nanometers to meters, used that in my wavelength, so I did speed divided by wavelength to get frequency. I then plugged it into E equals hv using Planck's constant and frequency, and because it wanted per mole of photons, I just directly went into multiplying it by Avogadro's number, 6.022 times 10 to the 23rd photons per mole. And I got 295,000 or 295 kilojoules per mole. So we know that electromagnetic radiation has wave properties, but we have also seen in experiments such as the photoelectric effect that it is best to model it as particles called photons. So it can be expressed as a wave or particles. How can electromagnetic radiation be both a particle and a wave? Well, in part, we're facing limitations in language. The words particle and wave accurately describe things encountered on a macroscopic scale, but we're trying to use them to model something, specifically electromagnetic radiation, that is not fully explained by either term. So no single experiment has yet been done to show electromagnetic radiation behaving simultaneously as a wave and a particle. Scientists now accept this wave-particle duality, that is, the idea that electromagnetic radiation has the properties of both a wave and a particle.